The socket layer. Here the kernel collects the new data written to a TCP or UDP socket via the read function from a socket, dequeuing the packet from the socket receive queue, see figure 4, to match the use of IPv4 in the egress. We use an AF address family INET receiving socket, and the function sysReceiveV enables this, first calling sysReceiveFrom to look up the socket. Then it calls sockReceiveMessage to read from the socket and passes the received message through Linux security modules. So the question here is, what is passed through the Linux security modules? So sockReceiveMessage reads from the socket, passes the received message or data through these modules, and that is similar to the egress. For IPv4, INET receive message calls either TCP receive message or UDP receive message, and this is in contrast to sock receive message. So if you wanted to note these two, they dequeue the packet's content and write it, so these two, they dequeue the packet's content and write it to user space buffer. So whether it's UDP or TCP, it gets written to the user space buffer. So for an example, an array on the heap, in that case it's getting written here. Finally, they free the skbuf. So here's our nice picture in the conclusion section. You can pause here and really soak this in. It's a great one. The description reads, an overview of the most important functions in both egress and ingress for UDP, as described in section 4. So the conclusion, this paper presented how a packet traverses the Linux kernel for TCP, IPv4, and UDP for IPv4. Figure 5 illustrates a recap of the packet egress and ingress path, highlighting the most important functions of each layer. Moreover, we described the intricacies of packet processing, including routing, filtering, and queuing mechanisms employed by the Linux kernel. Furthermore, we have seen how the different layers in the kernels communicate. By leveraging this knowledge, network administrators and developers can make informed decisions when optimizing network performance, designing security measures, or troubleshooting networking issues. Overall, the observed changes to the existing literature are primarily enhancements rather than rewrites. For example, refactorings or security improvements. A prime example is the choice of initial sequence numbers for TCP. For security reasons, the kernel authors revised the underlying hash algorithm multiple times. And the conservative changes make sense as the protocols remain mostly untouched while the impact of errors is high. Performing a similar analysis for multipath TCP or QUIC is future work. That's awesome. I will try to read that future work when they come out with it. And like in the last videos, I will paste the URL to this document and you can go through the references if you'd like. I think that was just such a great paper. Thanks for watching.